So let's step back for a moment and go back in time and look at our circus cannon driving down a hill. The reason I wanted to go back through this again, number one, is that you've got to remember how to solve free fall problems, or generally speaking, kinematic motion problems, where we use our kinematic equations to solve for the motion of objects and the position and velocity and acceleration at any time for objects under constant acceleration. So, but more importantly, it refreshes our memory on rotated axes. So let's just go through this quickly and refresh our memory on this. So I'm going to go through the situations where we have a truck going down the hill rather than a flat road. In the first case, we have the truck moving at a constant speed down a hill, and the cannon shoots off. And then the second case is the truck, rather than going at a constant speed, actually starts out at 20 miles per hour and then accelerates down the hill with its transmission in neutral, and lets gravity pull it down the hill and accelerate it. So how do we solve this? Well, we set up a simple diagram. We have the truck as a truck and the cannonball starting at the same location up here. We're going to set up our axes, our initial conditions, and I'm going to do this initially using our traditional axes for x, y, which would be along the ground and vertical. So this is a right triangle here, but not a special right triangle that I've drawn. It's a ramp. I gave you a 120 meter long base and a 50 meter high side here. You'll notice, if you know your geometry, this is a Pythagorean triple, so our third side is 130 meters. And if you really wanted to, you could figure out this angle here is 22.6 degrees. But it turns out, and I'll let you figure out why, you don't need to calculate this angle when you're doing any part of this problem, unless it asks you what the angle was. It turns out you can do something else to use that if you're clever. So I'll let somebody figure out how to do that. Maybe you can get some bonus points, especially if you do this on an upcoming quiz. So our traditional axis that we draw, we'd use the ground and we'd use the y-axis. And so I'm just going to use tradition here to do this problem first. And then we'd come up with initial conditions for each one of the objects, starting at this point up here. So we'll start out with our initial positions. So we were also given an initial velocity of the truck is 20 miles per hour. And remember, the ball is in the truck, so it also has that 20 mile per hour velocity as well. And that's the velocity of the truck as it's moving down the hill. And the ball, when it launches, is perpendicular to my surface. Yeah, it's normal to my surface. I can use the word normal again. And so the initial velocity of the ball will not only use the initial velocity of the truck, it'll also have an initial velocity in this direction. And you'll notice I've drawn these two in purple because we need to add those two together. And just remember, the ball has both of these components that have to be put together, and the truck just has the one. And we also have acceleration acting on the ball downward. The truck is in the first case moving using the engine to keep it at a constant speed of 20 miles per hour. So there is no acceleration for the truck, but the ball, once it's flying in the air, is going to be acted on by gravity. So here are initial conditions for the initial position for the truck. We're at 0, 50, and we've got to figure out the initial velocity of the truck. And here's our velocity vector. I just shifted it over because I'm going to decompose it off to the side. So I used h, that's the hypotenuse. So the hypotenuse of this vector that I'm breaking down is 20, so I've got to break down these two pieces. And you can feel free to use SOHCAHTOA to do that, and you can come up with these values for the velocity of the truck. And you notice we're going into quadrant 3, so both of these are negative. All right. So that's the initial position and velocity of the truck. And what about the acceleration of the truck? Well, the acceleration, it's moving at a constant speed down the ramp, so it's moving down constantly and to the left constantly without changing its speed in either of those directions, so those are going to be zeros. So our acceleration in the x and y are zeros. And so those are our initial conditions for the truck, and we can come up with motion equations for the truck by plugging them into equations. These are equations 5 in the x and the y. You could potentially use equation 6 or equation 8. but I'm just going to stick with equation 5 for now. Now, what about the ball? For the ball, it's starting at the same location the truck is, at 0, 50. So for the velocity of the ball, we need to take both of these velocity vectors and include those in our initial velocity of the ball. So we've already broken down one piece of the velocity for the ball, which is the piece that the truck is moving along at. We've also got to add in this normal component to the surface of our ramp. And so we're going to have to break that down to match up with our x and y axis as well. So let me shift that over to the left. So we're going to have an upward piece of that and a leftward piece of that. And be careful, because notice that our angle here is not in our traditional horizontal position to use our x and y components with cosine and sine. We're actually going to have to use sine and cosine for these because our opposite matches up with the x now. And so when we actually pull this information out, we've got, here's the component from the cannon, and here's the component from the truck for both of these situations. And we'll add those up. And remember, our acceleration of the ball is simple. It's just this one acceleration vector right here. It's in the negative 9.80 meter per second squared vertical position. So that's an easy one in this case. And when we add up our components for our velocity, they turn into negative 40. There is no acceleration, so that's a 0, and our initial position is 0. So very simple equation for the x component, and here's our equation for the y component, which contains half of our gravitational acceleration and then our two components for our velocity. So there's our equation, our motion equations. It leaves equation number 5 for our position versus time in the x and y direction. The question is, how do we solve this? Well, I didn't actually go through the full solution process for this, but that's all the information you need to solve. And I'll leave this up to a bonus if somebody wants to go through, and feel free to use these equations to come up with a clever solution of how you can see where this ball is when it reaches the ramp again. So that's a bonus if you go through and solve this on your own piece of paper nice and neatly and show me how you did it. So feel free to do that and turn that in next class. But there's an easier way to do this. All right, and the last problem, the question is, how do you solve that? It's a little bit tricky. If we rotate our axes, things work out much nicer. And the question is, why do we rotate axes? Well, you'll notice that we have two perpendicular components here that are vectors, and we have one vector here. And so when we selected our initial axes, our xy axes, these two vectors didn't line up, and this vector did. So we had two unaligned vectors and one aligned vector. If we rotate our axes, then that's going to make our problem a little bit simpler, because two of our vectors will be aligned and one will not be. So it'll reduce the number of vectors that we have to decompose. And so that's really the reason why you'd rotate axes. If the new alignment lines up with more of your vectors than it doesn't, then you'll save yourself some time and trouble, and you might be able to see things a little bit easier, as you see in this problem. So we're going to go ahead and we're going to realign our axes to line up with two of the three vectors to make it easier for ourselves. Alright, so now let's go ahead and put our vectors back in here. Now you'll notice the initial velocity of the truck is aligned with our x-axis, and the initial velocity of the ball, at least the y component of the ball, remember the ball also has this component of the truck's motion, is also aligned. So those ones we will not have to break down. The only one we'll have to break down is our gravitational component, which is right here. So now we only have to break down one thing rather than two. Alright, and so we drew a rotated axis, and we're just going to go through this problem again. And for the truck, it's very easy to do this because we're starting at 0, 0, and so our x and y components are 0. Our initial velocity of the truck is 20 meters per second in the x only direction, and we're not accelerating on the ramp, we're moving at a constant velocity. So we get a very simple equation for our equation 5, and a 6 if you wanted it, is positive 20t. No acceleration, no initial position. In the y direction, it's even easier. We don't have any starting component in the y direction. We're starting at 0. We don't have any y component of the velocity. The truck's not moving up and down with respect to the surface of the ramp. and we don't have any acceleration. The truck is not accelerating in the y direction, so there is no y equation. Much, much simpler. For the ball, let's take a look. So for the y direction, once again, we're starting at 0 and 0, 0 for the ball. And our x direction, once again, that ball, the velocities are given to us right off the thing. We don't have to decompose anything here. So we're moving 20 meters per second in the x direction. That's along the surface of the ramp. And we've got 30 meters per second. That should be an S there, sorry. Perpendicular to the ramp in our y direction. Easy. And our assumption here is that we're in free fall, so the ball has an acceleration that's acting downward. Now, downward is going to have to decompose. It does not match with our xy axis, so we do have to do a little bit of work here. Not a problem. So I'm just going to draw another parallel line through the end of my arrow here, and now you can see I need to break this purple vector down in terms of my xy axis that I chose here. So here's the perpendicular piece and here's the parallel piece. So you got to be careful when you do these decompositions on a rotated axis. Just draw lines parallel to your x-axis and perpendicular to x-axis to box in this arrow. And there's my perpendicular, or my vertical piece, my quote-unquote vertical piece, my y component, and here's my x component. All right, you'll notice one component acts into the ramp and one component acts down to the ramp. This component acting down the ramp is accelerating the object in the direction of the surface of the ramp, and this component is accelerating the object in the direction perpendicular to the ramp. And using my 22.6 degree angle, and remember there is a way to do this without using any angles. You can use the side lengths somehow of our Pythagorean triple. If that's 22.6 here, this is 67.4 here, and this is another right angle here, so this also must be 22.6. Don't forget this geometry here. So that theta there and that theta there are the same. So, and just be careful that once again, this component, which is our x component, our x-axis, is actually aligned with the opposite of our reference angle. So that's going to pick up the sign. And so we've got our gravitational acceleration g times sine of theta acting in the x direction and g cosine of theta in the y direction. And so I'm plugging that in, and here's what you get for your answer. So I get 3.77 meters per second squared down the ramp that the ball is accelerating in, and it's acting toward the ramp with negative 9.05 meters per second squared of acceleration. All right, and here's our new equations. So it took a little bit of work for the ball, but not bad. We only had to decompose one vector. So now the question is, how do we answer this question? So the question is, when this ball reaches the ramp again, in other words, remember, this x-axis represents a height of 0 when we're back down to this level of 0. So when my height is 0, where's the ball? Well, the height of the bullet and the truck are matching. They're in the same system now. They're with respect to the surface of the ramp. And so this the x component is all we really need to look at here to see if the x component matches, then the ball will land directly into the cannon again. And the y direction is just the height above the ramp. So when this gets back down to the ramp, the question is, are the x's at the same value or not? Well, they partially match, the 22 matches, but you can see the x position of the ball has certainly outpaced the truck by the time it gets down to the ramp. At the bottom of the ramp, it's got this component to take into consideration as well. So the cannonball is going to be way out in front of the truck when they return to the ramp. So let's take a look at problem 2. Asked what happens if we put the truck in neutral. We're start at 20 meters per second, but in neutral, so now we're going to let gravity pull the truck down as well. Well, now the truck has the same component of the acceleration that the ball does, because that component is pulling me down the ramp. And so here's my new equations for the truck. It's positive 3.77 t squared plus 20t. Now you'll notice our x components match up, and so the positions, the x positions of both the ball and truck are going to match as the truck is accelerating on the ramp. The ball is going to be right over it at all points in time and drop right in. So it turns out to be an easy solution. So using a constant So in summary, we were able to use a rotated axis to make this a much simpler solution. It takes less work, and you can visually see what's happening a little bit easier than you could when you didn't rotate the axis. And we'll see that we can use